Camera's over there. Hey, Mark. Hello, Mark.
Hi, Vanita. How are you?
Good. How are you?
Very well. Thanks for
How are
having
things
me.
over in Wisconsin?
Yeah, beautiful day here.
Great. Yeah, here too. It's not too bad. A little warmer. So your slides are okay, ready to go?
I think it should work. Yep. Would you like me to project them now?
You can test it out. Yeah, sure.
Good.
Yep. Looks good.
Okay, fantastic.
I'm seeing the projector light, but I think we can get started. You ready?
Anytime.
Great. So welcome back, everybody. So this is the third quantum computing implementation session at this conference, session 9, I believe. And so first, it's my great pleasure to welcome Professor Mark Eriksson from the University of Wisconsin-Madison. So Professor Eriksson is the Jarn Bardeen Professor of Physics at the University of Wisconsin-Madison. He received a BS with honors in physics and mathematics in 1992 from the University of Wisconsin-Madison, and an AM in 1994 and PhD 1997 in physics from Harvard. His PhD thesis demonstrated the first cryogenic scan gate measurements of a semiconductor nanostructure, something that's very important for semiconductor quantum computing. He was a postdoctoral member of technical staff at Bell Laboratories from 1997 to 1999, where he studied ultra-low density electron systems. Professor Eriksson joined the faculty of the Department of Physics at University of Wisconsin-Madison in 1999, and his research has focused on quantum computing, semiconductor quantum dots, and nanoscience. So with collaborators, he demonstrated the first quantum dot in silicon germanium occupied by an individual electron, and performed the first experiments to demonstrate the quantum dot hybrid qubit, which is a 3-electron qubit in a double quantum dot. So Eriksson currently leads a multi-university team focused on the development of spin qubits in gate-defined silicon quantum dots. So the goal of this work is to enable quantum computers, which manipulate information coherently, to be built using many of the materials and fabrication methods that are the foundation of modern classical integrated circuits, as we've heard throughout the conference. Professor Eriksson was elected Fellow of the American Physical Society in 2012 and AAAS in 2015. So it's a great pleasure to welcome Professor Eriksson. I've known Mark and his work with Sue Coppersmith, who we heard from on Monday, and Mark Friesen over at Wisconsin for a while, and it's been great, and it's great to have him here. So thank you. Take it away.
Thanks very much, Vanita. Thanks for having me. It's a real pleasure to be here. Some of those dates, like 1992, sound like a long time ago now, but nonetheless, they apparently are accurate. So thanks very much for that. What I'd like to do today is talk about semiconductor quantum dot qubits, and specifically cavity-based measurement and coherent spectroscopy. So I'm happy to take questions at any point. The first thing I'd like to do is mention that in physics at the University of Wisconsin, we're hiring this year. And perhaps that's of interest to some people in person or on the line. And if not, perhaps it's of interest to colleagues, especially postdocs who you may know. So let me just say we're hiring in condensed matter physics. We have an unusual position. It's an endowed chair of assistant professor. And so that's in condensed matter, and with a heavy emphasis on quantum information as well. And then we're also completing a cluster hire in quantum science and engineering. This position will be in physics, so I guess you would call it a professor of quantum science. It can be at any level, assistant, associate, full. So please feel free to contact me or point people in my direction, or Bob Joint, who I believe is there in person, can answer questions as well. So I hope that's of interest. I would like to start by just taking a quick look at silicon-based quantum dot qubits. We've covered a lot of ground this week. I don't need to give a lot of introduction to semiconductors, and certainly not to quantum computing. Let me just emphasize a couple of things that I think are great to keep in mind. One is that there's already some really neat evidence coming out of places like UNSW and TU Delft that semiconductor quantum dot qubits can be operated at temperatures above dilution refrigerator temperatures. And I think this is really promising for the future. Everything I'll talk about today is at dilution refrigerator temperatures, but it's all laying the groundwork for a future that may indeed be warmer than 100 millikelvin or less. The second thing I'd like to emphasize is that already people, including some work in my group, but other groups as well, are integrating classical semiconductor devices, FETs, and integrated circuits on the same chip with quantum dot based qubits. And that's just really exciting for me. I think it's one of the really interesting paths and enabling technologies for scalability, as is the whole idea of 3D integration, which I'll mention in more detail today. So there's a large body of work going on all around the world in many areas of quantum computing, obviously, as this conference has shown. And I just want to emphasize some of the things that make semiconductors interesting from the perspective of scalability. So we heard some really nice talks earlier this week about increasing numbers of qubits. I'm going to talk about techniques for working with these qubits. So we're going to be working with individual qubits today in this talk. And as you can see on this slide, there are actually 4 different types of qubits that live in quantum dots. This is similar in many ways to other qubit technologies, superconducting qubits. Essentially, every qubit type has a variety of specific implementations, and semiconductor quantum dots are no different. What I want to emphasize about these, and you won't really need to know too much about any individual implementation, because all of these qubits are measurable by charge projection or polarizability in a double quantum dot. What that means, of course, is that you can take qubit state information and map it onto a charge difference, depending on which state you're in, or map it into a polarizability difference, depending on which state you're in. If you do either one of those things, you have the ability to measure the qubit and to do so relatively rapidly. And that's really what I'd like to focus on today. So the 2 things I'll talk about are, first, a new method for measurement and readout using dynamical longitudinal coupling to an on-chip circuit QED resonator. You can find information about the device we're using in this paper by Nathan Holman and collaborators, published earlier this year. And the work I'm going to talk about is not on the archive yet, but it will appear there shortly in a paper with first author by Joel Corrigan. And let me say right up front that this is a really wonderful collaboration with MIT Lincoln Labs and our next speaker, Will Oliver. The second thing I'd like to talk about today is coherent microwave driving between excited states in these qubits. This is really important. It's something that atomic physicists and AMO physicists more broadly can do all the time. And it's the type of thing that's just getting started in electronic quantum dots. It's going to be, I think, a really powerful technology. We're at the very initial stages, as I'll show you, but the capabilities are really starting to grow. As a what I call a physics bonus, I'm going to actually show coherent control of Vigner molecule states, and I'll explain what those are. Let me emphasize right up front that I'm not recommending Vigner molecule states for quantum computing, but life is short, and we have to enjoy really fun physics when it shows up. And so that's the system that we're going to use for today's demonstration. And I think the real important takeaway for quantum information is this ability to drive coherently between excited states within a quantum dot. So those will be the 2 topics for today. And I'm really looking forward to talking to you about it. So before I do that, I want to acknowledge the people who did the measurements in my lab. So the data you'll see today was acquired for the most part by Joel Corrigan, who's highlighted here. This picture was taken at the Silicon and Quantum Electronics Workshop in Spain. And the 2 samples that we'll talk about were fabricated by JP Dodson and by Nathan Holman, both now at HRL Laboratories. They've, of course, done fantastic measurements themselves on these and other samples, but it'll be Joel's measurements that take center stage today. Those measurements were done in collaboration with 2 younger students, Ben Harpt and Peter Marciniak, who are in my group now. And when the time comes, these are 2 just absolutely spectacular young scientists. So with that, I would like to dive into the first topic today, which is a new method for measurement and readout using dynamic longitudinal coupling in a circuit QED resonator. So I'd like to refer back to what by now is well established. I first learned about this type of technique in a really nice paper from Jason Petta's group all the way back in 2012. And I'll just put up a highly schematic representation of conventional readout. It's recent, but now I think very well established by many groups around the world. And so what you can see here is a double quantum dot coupled to a cavity. And this cavity can be on the same chip or it can be on a flip chip bonded to that main chip, which is what you'll see later today. And that cavity obviously has a nice resonance in it. And if we change the polarizability of this double dot, that's going to change this resonance. It will shift, it will change in amplitude. And as a result, you'll be able to read out changes in polarizability of this double dot. Now, what's really nice is that the double dot polarizability changes anytime you're about to change the charge distribution on the dot. So for example, if you're about to transition one electron from the right dot to the left dot, that creates a polarizability if you try to push that electron back and forth. Similarly, if you try to empty an electron to a lead, that creates a change in polarizability. So one can, in fact, acquire charge stability diagrams, which if you live and work with quantum dots, you know is sort of the core measurement that one gets to tune these things up. So this type of readout works really very well. Now, one of the things that one has to do for this readout, of course, is have the cavity. One needs to drive the cavity, measure the cavity, and one has to couple the qubit and control the qubit connected to that cavity. Those are the core elements. What would be nice is if one could get away with fewer high frequency lines. That's one very practical motivation. And in fact, one can try to do that if you drive the cavity and the qubit from the same gate. So if you drive a qubit with a gate tied to the qubit that also has a coupling to the cavity. So I'll show you today that this works in a very practical sense. It's highly effective, but much more interesting than just saving yourself a gate is that it enables this dynamic longitudinal driving that I mentioned, which really enhances the rate at which and the signal to noise with which you can do the readout of this qubit system. Now, that's what I'll show you today. This actually offers up the prospect of using a global gate to drive both the cavity and more than one qubit simultaneously. And this is reminiscent, this idea is reminiscent of some global driving that's been done at the University of New South Wales, looking at qubits also in silicon in that case, where the qubit is brought in and out of resonance of a global field. And I think this approach, driving a qubit coupled to the cavity, offers the possibility for doing the very same type of thing, but in a circuit QED setting. So the type of sample that I'll use for this demonstration, and I should really say that Joelle will use for this demonstration, is a quantum dot formed in a silicon-silicon germanium heterostructure. I won't go through the fabrication details. They're all described by Nathan Holman and collaborators in this reference on the bottom. And you can see an optical image of the type of chip on the left here. This is what the gate structure looks like. So we're able to form a double dot in this structure. And we have a really wonderful collaboration with MIT and Lincoln Labs, the group of Will Oliver, and I'll show you all the rest of the names at the end today, where they do flip chip bonding. They've, of course, done very complicated flip chip bonding. I think we're on the simple end of what they're doing, which is two chips bonded together. And let me just say that they are true professionals at this. So what they have made for this collaboration is a titanium nitride cavity on a cavity die that's flip chip bonded and allows us then to have access to a resonator whose properties depend on a fabrication flow, which is independent of the silicon-silicon germanium fabrication flow. And if you've done any clean room work, this ability, I think you'll really appreciate this ability to factor the problem and compartmentalize and think first about how do you make something on silicon-silicon germanium, what's your thermal budget, what are your processing conditions there, and then take advantage of making a beautiful titanium nitride resonator, which has high impedance, in this case about 575 ohms, for the waveguide that we form the cavity out of in this case, and think about its fabrication on its own without the constraints that you would otherwise have. We've made cavities both ways, and I really appreciate the flip chip bonding approach. Okay, so if one takes this type of sample, one can do the standard dispersive readout that one would expect to do. And I show you 4 different examples of that here. And in all these cases, one is driving the cavity through various ports on this chip. And there are many such ports because we have many gates and 3 connections actually to the cavity on the titanium nitride chip itself. And so if we do that, we see exactly the type of dispersive signal that I showed you earlier in the talk. Now, what I'd like to emphasize is that one can drive the cavity and the qubit at the same time. And so in this case, what you can see is that the cavity, which cuts right across the middle here on the chip above, of course, that cavity couples to the double quantum dot through a gate that comes very nearby to the double dot. That's essential. But at the same time, that gate has a capacitance to all the other gates in the quantum dot. And if one chooses, one can use a gate that drives the detuning of the double dot. The detuning, of course, is the relative energy of the 2 dots. It's an attempt to move, changing the detuning is an attempt to move an electron from one quantum dot to the other quantum dot. And so one can do that while simultaneously one is driving the cavity with that very same signal. And that's a really powerful approach, as I hope I can convince you on the next couple of slides. So what you see on the lower left here is the type of signal you get if you simply drive the cavity and tune the quantum dot to what we call the polarization line, to the point in gate voltage space where you're just about to move one electron from, let's say, the right dot over to the left dot. And at that point, it's very easy to slide that electron back and forth. That creates a change in polarizability. It creates an enhancement in the polarizability of the environment near the resonator. And that creates a little shift in the resonant frequency, and that creates a little dip in the transmission through that cavity. Now, if you simultaneously drive the double dot, you see something really remarkable. Instead of a little dip, you can see a large enhancement. You can see that plotted in a line cut here. You can see it on a grayscale plot at this point. And what I'd like to emphasize here is that, first of all, the signal to noise is greatly improved. If you're driving the double quantum dot, detuning at the same time as you position that double dot on the polarization line at the point where you're moving an electron from the right to the left or vice versa. So that's really advantageous. Now, when you first see this type of data, as any good physicist, you're first thinking about energy conservation. How can we get more energy out of the cavity than we're putting in? And of course, the answer is this driving of the quantum dot is in fact pumping energy into the cavity at the same time, but it's doing it in a very specific and controllable way that depends on the state that the qubit is in. And this is really the take-home point for this first part of the talk. Using dynamical longitudinal driving of the qubit, one can pump energy into the cavity for readout purposes dependent on the state of the qubit. And that's really powerful because that gives you a knob that you can turn up when you want to do measurements. So we can characterize this, of course, in many ways. I'll show you just a little bit of it today. Again, it will appear on the archive shortly. One of the things that you would want to think about first is, well, if you're driving the double dot, and I call that detuning driven here in these plots, so we're driving the detuning between the two double dots, what you can do is change the tunnel coupling. And what you would expect is if that tunnel coupling is very small, you don't see much of a response. And as you turn up that tunnel coupling, you see a much larger response. And that's exactly what you find in the data. And interestingly, if you make a comparison plot where you're not driving the detuning, there's very little change in the type of readout that you have. So it's very clear that this dynamical driving of the qubit has a big effect on the qubit readout. Here's a little movie just showing you that as you change the tunnel coupling, you can see the evolution of what this signal looks like. The movie is fun, but it's hard to follow in detail. So let me just instead move forward and show you that you can really use this technique to measure whether or not you're occupying the qubit ground state or the excited state. And so for this demonstration, Joelle tuned up a qubit to use and used a Larmor pulse. in order to occupy that qubit excited state. And so the pulse is shown right here. It's again driving the detuning. So what is plotted here by these lines is the energy as a function of this detuning between the double dots. And when you move one electron from left to right, you of course switch the ground state. That electron does transfer over, and that's exactly what we call the polarization line. And that's very easy to measure because if you leave the system in the ground state, you tune to that point, you get a very large change in polarizability, as I just mentioned. Now, the advantage of the Larmor pulse is it's one way to generate population in the qubit 1 state. And if you do that, you should then be able to sense the polarizability at this excited state anti-crossing. You will only see this if you occupy that excited state, if there's some non-zero probability in the qubit state to be in the 1 state. And you can see that very nicely in this color plot here, where the polarization line is always visible here, just above 4 millivolts on this plot, and up at 6 millivolts at the voltage location where the excited state anti-crossing occurs. You only see that come in if your Larmor pulse is strong enough to actually occupy that state. And so this is a very nice readout of which qubit state you're occupying. We can, of course, do that in the other direction. So we can pulse the opposite way. That's the advantage of a double dot. You always have 2 qubits at your disposal there. And what you see is that line appears at a different voltage, as it should, because the excited state that corresponds to the qubit 1 state is not the same in these 2 double dots. So that's one nice application of this type of readout technology. So I'll close right now so that I can move on to the second topic of the talk today by just emphasizing we've got a really nice theory collaboration with Rusko Ruskov and Charlie Tahan at the Laboratory for Physical Sciences. I can't possibly do justice to their theory, but let me just say that Rusko has worked out really very nicely what line shapes are expected from this dynamical longitudinal coupling. And Joel and Rusko have worked really carefully and tirelessly, I would say, to understand how that fits the data. Can be used to fit the data in these experiments. So I'm happy to talk much more about this at some later date if people are interested. So I'd like to shift gears now, and for the remaining part of the talk today, I want to talk a little bit about coherent microwave driving between excited states. So the first part of my talk was really focused on a technology that will enable readout in a faster and with larger signal to noise. The second part is focused on a different, really important question for quantum computing, and that is, do we have the ability to drive between excited states within a semiconductor quantum dot, to drive those transitions with microwave pulses, and to do the type of manipulation that people are used to doing with extremely narrow line widths in atomic physics. And of course, our line widths are nowhere near the type of line widths that you can get in, say, a neutral atom qubit, or with some clock transition, orders and orders of magnitude broader lines. Nonetheless, these line widths are getting narrower, and it is becoming possible to do exactly those types of manipulations in the very first initial steps. And as I promised, I will say a few words about Vigner molecules in this context. But really, it's the driving from excited state to excited state that I think is so important for quantum computing. Okay, so I have to say a few words about what these states might be in silicon germanium quantum dots. And so this will go very quickly. A quantum dot is a potential well, and obviously one has orbital states. Each of those orbital states, of course, has spin states. The important thing in silicon, which is not obvious if you don't work in it all the time, is that there is a Valley degeneracy. So the silicon conduction band has a minimum that is not at the center of the Brillouin zone. It's not at the gamma point. In the types of strained silicon quantum wells, there are actually 2 minima. They're in the growth direction, so in the KZ direction, and that gives you a doubling of the states. So every orbital and spin state has a partner corresponding to a different spot in the Brillouin zone. And that degeneracy between those 2 states arising from the silicon band structure is split. And it's split by all sorts of really interesting physics, which you heard about earlier this week by Sue Coppersmith, who's a longtime collaborator of mine. And Bob Joint as well has come up with some really spectacular ideas for controlling that splitting. All you need to know for this talk is that that splitting exists. And in particular, that splitting can actually be the basis for a really interesting qubit called the quantum dot hybrid qubit. And that's a qubit that Vanita mentioned in her very kind introduction earlier. So that quantum dot hybrid qubit is a qubit that consists of either 3 or 5 or more electrons, but in all cases, the qubit is really defined by the state of a 2-electron quantum dot. And the 1 and 0 states of that qubit are either the singlet ground state, so both those electrons in the lowest energy state of that dot, or a superposition of triplet states, so that therefore involving the first excited state in that quantum dot. And so the energy of the qubit really is just the energy splitting of the quantum dot that happens to have 2 electrons in it. It's a really powerful qubit. The theory idea was came from Sue Coppersmith nearly 10 years ago now. It's amazing how time flies. So in order to read out this qubit, as I mentioned earlier, it is really convenient to either project that state into either a change in polarizability, which I discussed earlier, or to a change in charge state. And so for this part of the talk, we're going to project that qubit state onto a different charge state. And that's where adding more electrons, so working with 5 electrons instead of 3, is really useful. And just schematically, you can see that the readout window here, if you add a few extra electrons, becomes much larger. And that's because you're essentially doing something like shell filling in the left quantum dot. Again, I'm happy to talk about that in more detail. Okay, so very quickly, one can do really spectacular measurements by making use of qubit manipulation. And so one of the things you can do, for example, is you can map out the energy versus detuning diagram for a double quantum dot. I'm showing it here for a very simple qubit where there's really only one excited state of interest in the problem. I'll change that in just a moment. But what you can see here is that if you ramp over adiabatically, one can apply a pi halves pulse, one can change the detuning, one can bring it back, one can then recombine and project out. And when you do that, you get a really nice measurement, which is essentially an interferogram of the qubit. And by Fourier transforming this and extracting those frequencies, one can get the qubit energy difference between the 0 and 1 state as a function of detuning. So this really lets you pull out experimentally what your qubit Hamiltonian is really doing. So if we do that, we can then ask ourselves, well, what happens if you have more than one excited state around? And the easiest way to get that, and the way that I'll use today, is to turn on interactions. And the way, of course, you turn on electron-electron interactions is not by changing the charge of the electron. That's for the theorists. I'll show you that in just a slide. But experimentally, you do that by softening the quantum dot confinement potential just a little bit. So you bring that single particle non-interacting energy spacing down a little bit so that the electron interactions are comparable to that value, or of course, larger than that value. And if you do that, instead of getting a really simple picture where you think about, okay, there's an orbital ground state, there's a valley splitting, each of these is spin degenerate, one mixes in a huge number of high-lying excited states because those electron interactions are so important. That gives a whole ladder of states that are accessible and inner energy range, which can be accessed via microwaves between, say, 5 and 20 gigahertz, which is a very convenient range. So moving forward for quantum information, again, one wouldn't need as many as I'm about to show you. 2 or 3 would be just great. But I'm about to show you a series of manipulations with 5 different excited states. Okay, so very quickly, how does one think about these Vigner molecule states theoretically? Well, as I mentioned, the theorists can turn the electron charge on and off. And if one thinks about 0 electron charge, one sees the non-interaction picture here. And you can see that down here at 0 electron charge, the first orbital excited state is somewhere up around 60 gigahertz for this particular incarnation of the simulation. This, of course, matches the experiment that I'm about to show you. If one then turns on that electron-electron interaction, those states actually drop in energy. And one over here on the right-hand side, where the electron-electron interaction is turned fully on, one sees a huge dense ladder of states. And there are little gaps in those states, and those gaps actually can be mapped back to the gaps in the single particle spectrum. But this bringing in a very high energy single particle states gives you a really nice, beautiful set of Vigner molecule states at low energy here between, as I mentioned, 0 and 20 gigahertz. Okay, one can make really beautiful plots. I don't have time to show all these and discuss them in any detail, but this is work done by Eriksson, who's now at UCLA, working with Mark Geyer. Ekmel did his PhD with Mark Fries and then Sue Coppersmith at the University of Wisconsin. And in short, the Vigner molecule states look exactly like you'd expect them to look. You get really nice charge separation. And then for this talk, the important thing is you also get a really dense set of states corresponding to these different charge separations. Okay, so the picture now has become much more interesting. Instead of just having a single excited state in the frequency range of interest, one can have a great number of excited states. And this on the right, with the benefit of hindsight, is actually the spectrum that I will show you in the next 5 or 10 minutes as I finish up the talk here. And so this is a fit to real experimental data. And what you can see is that we have softened the confinement in one of the quantum dots so that there is this ladder of low energy excited states that we can manipulate. And in the other dot, we have maintained the confinement so that we have a nice large readout window. What that does is it lets us project all these states onto a charge difference. If we're in the ground state, that stays in the blue line. That's the 4-1 state. If we're in an excited state, that goes over to the 3-2 state, no change in charge. And that charge difference is really easy to measure. Okay, so if one looks at this from an experimental perspective, what you can do is you can measure the dispersion as I showed you just a few minutes ago. And so what you want to do then is think about, well, what is the energy difference between the blue state on the bottom and all the other possible states in the system? And there, of course, are many ways to do that. You can subtract the blue state from these top 5, which is what I just mentioned, or you can start in, say, the light brown state here and subtract its energy difference from those above it. And that's what we'll do today. And those two cases are shown on the upper right and the lower right here. And I'll show you that we can measure all of these energy differences, except this very last one, which corresponds to ground state to this 1 state. It's just a little too low in energy for us to access. Okay, so to get to the punchline here, what Joelle Corrigan did midway through her PhD, and this work just appeared in Physical Review Letters about 2 months ago, she was able to do Ramsay spectroscopy of both the ground state up to that 5th excited state and from the 1st excited state to that 5th excited state. And you can see that the dispersion is quite different in those cases. As I mentioned earlier on the previous slide, we can, from the ground state, see a really big upturn in energy as you go through the anti-crossing. But of course, the 1 state does not bend down. And so the difference in energy between the 1 state and the 5th state actually stays quite shallow as you move forward. And if you don't listen to anything else I say for the rest of the talk, that would be fine, because right here is the key take-home point. What Joelle is doing is she's doing a Ramsay fringe experiment between the 1st excited state of the quantum dot and the 5th excited state of the quantum dot. She's done many others as well, but already that right there is the key new technological advance, which I think is going to be really important for quantum dot qubits as we move forward. Okay, so having said the main point, I'll go really quickly through the remaining slides here. Joelle was able to use Robby oscillations to look at crossings between these 2 energy levels. She was able to use Robby to go in and individually address many different levels here. These data points are mapped onto both energy and to tuning. And you can see that each point or set of points lines up with a different energy level in the spectrum. So these energy levels are, of course, fit to these points, but there's a lot of data here that Joelle is fitting simultaneously in order to get self-consistency in this device. So if we look at all of these things together, you can put all the data on one plot. And I think it becomes really convincing that one can go in and do interference measurements that allow you to track where these excited states are moving as a function of detuning in this coupled double dot system. Okay, so with that, I'll just say one more thing for the experts, and then I'll be happy to take some questions. One of the things that we found was really essential when doing these experiments is to take advantage of the ability to measure what your fridge wiring is doing from top to bottom, so room temperature all the way down to the mixing chamber. And so, for example, here's an S21 measurement as a function of frequency out to not quite, but nearly 20 gigahertz. And then to think about the pulse that you want, in this case, it was a very simple trapezoidal pulse, and then to use Fourier analysis to induce pulse corrections into a very fast AWG so that we actually apply the pulse in teal on the right in order to get at the mixing chamber something which is much closer to the pulse in yellow, which is what we want to start with. And I think without this type of technology, this would not have been possible. And this was a really nice collaboration between Joel Corrigan in my group and Brander Thorgrimsson, who is now at UNSW, working with Michelle Simmons there on donor qubits. So with that, I will wrap up and take questions in just a second. I've already mentioned many names from Wisconsin over here, including some spectacular theory collaborators of mine, Bob Joint, Mark Friesen, Ekmel Eriksson. I did not have a chance to mention Jose Carlos Abadillo Uriel, and my experimental colleague, Robert McDermott. Sue Coppersmith is now at UNSW. We received material from Lisa Edge and Clayton Jackson of HRL Laboratories. I mentioned Will Oliver's group, spectacular collaborators on that. And I've also done a lot of work recently with Sandia National Labs, Lisa Tracy, Deanna Campbell, the team at TU Delft, and Amir Yacobi at Harvard. And so with that, I will thank you very much, and I'd be happy to take any questions.
Thank you so much, Mark, for that amazing talk and great results. So questions from the audience? So in your excited state driving, what do you see as sort of the limitation there? Is it, is frequency selectivity enough to sort of target the transitions that you want, or are there, issues beyond that?
Right. So I do think that what you just said is very likely going to be enough on frequency selectivity. That's what Joel used in these experiments. And what we have not yet done, and what we're going to be working on in the coming months, is doing Robby from one state to another, and then Robby again to a higher state. So in this case, we occupied that first excited state via other methods, non-adiabaticity of an initialization pulse. And that showed that we were able to access these different levels. But that was just a starting point. And what we need to do now in terms of making this a really useful technology, for example, for initialization and for readout, and possibly for gates as well, although I think the promise for initialization and readout is more important. At least that's my best guess right now, is to actually do those Robby pulses between various states. So that's something we're going to be working on.
Great, thank you. And also, you showed the where you, for strong enough electron-electron interactions, you get these Vigner, multiple states, ground states. How strong is that? Like how small is the the electron distance?
Right. So in these experiments, the quantum dot diameter is about 40 nanometers. And what's really, and so the electrons sit in there together. And when you would get the Vigner molecule states, they sort of separate onto opposite halves. And so a typical separation between the weight and the wave functions would be about 20 nanometers. So that's, I guess that's the shortest answer to your question, is about 20 nanometers. But I think I also want to add that it's surprising how easy it is to make this transition from non-charge separated states, which is what many of us think about most of the time when we're doing these experiments, to this Vigner molecule regime. So we had to soften the confinement. And when we did that, it's really only relatively small changes in gate voltages that allow that wave function to extend out just a little bit farther than it used to. And what happens then is that you cross, it's not a phase transition or anything, but you cross a threshold where really rather rapidly the spectrum goes from more or less single particle like to really in the Vigner limit. And to me, that was surprising. Maybe it shouldn't have been, but it was. And it was just really neat to learn that and to see how rapid that changeover can occur in the lab.
Great, thank you. Other questions? We have some from the chat.
Yeah, we have one of the online attendees, TK Sals, asks, to get the energy spectrum, can you use microwave excitation to map states?
Yeah, that's a great question. Absolutely, you can. And there are multiple ways to do that. The two I showed today were using Robby pulses and then taking advantage of those Robby pulses to do Ramsay fringe measurements. But there are many other ways, as you're referring to, that we can do that. For example, one can do photon-assisted tunneling, where you don't worry about doing a controlled rotation, but rather you simply hit the dot with a really powerful, well, not that powerful, but relatively strong microwave pulse. And actually, Jason Petta's group did that years ago, and he recommended that to me a few years after that. And we've done that. It's actually a really useful and powerful technique. And you can also just use what I call alarm or pulse. So just a rapid change in detuning. And we've done this for many years now. If you simply abruptly change the detuning, you will, through Landau-Zener Stuckelberg, Landau-Zener tunneling, I guess I should say, you will populate the full spectrum of excited states as long as your ramp time through all of the various anti-crossings is appropriate. And then when you come back, you will see all of the different frequencies overlapped. And we've been able to pull out, situations where we occupy quite a few different states simultaneously and pull out from the Fourier transform what's going on. So you have lots and lots of ways to do it.
Thank you. Yeah, still more time for other questions. We have more in the chat. That's it. So I have more of a general question on, you have this, NSF Center for, building modular systems, and I believe you're, a part of the, head of that. And so, we're building the program, and we're looking to sort of connect with these bigger centers. And definitely, from the perspective of my own research, that would be a great center to connect with, because we're thinking about modular systems with semiconductors theoretically right now. But so what would you have some, words of advice on the best ways to connect with that beyond, our usual discussions?
Yeah, absolutely. And so let me first just acknowledge up front that although I am involved in the leadership of QNext at some level, which is a DOE center, I'm actually not involved in the leadership of NSF HCAN, which I think is the center you're referring to. Mark Safman is the lead PI at Wisconsin on that, so I just want to give Mark his due there. But I can answer your question, of course, all the same. I think the thing to do is just to approach this goes for anyone, to approach the individuals you'd like to interact with technically. And then there are many ways to interact, right? Ranging from the types of casual discussions that you already mentioned to more formal collaborations. And that's something that I think, Mark Safman can speak to more directly. And I should also emphasize that HCAN, although Mark Safman is the Wisconsin lead on HCAN, the overall PI and the director of the HCAN Center is Brian DeMarco at UIUC. And David Oshalom is the overall lead for QNext. So there are a lot of quantum centers, as we know now. But yeah, thank you for mentioning that.
That's great. Yeah, and because I mention it also because, with our MS quantum computing degree, which of course you have one as well, and this conference is celebrating the start of it here. We have internship in between the 4th and 5th years in our program, as well as faculty research projects during the 4th and 5th years, in semester projects. So it would be great to engage with these institutes for, opportunities for students here. So that's basically, it's great to hear that if you have, programs that I know that you have some programs, but I'm just wondering, if there's, some specific ways to interact that way.
Yep, absolutely. Vanita, may I answer one last question from Emily Pritchett in the chat?
Absolutely, yeah.
Okay, so Emily, thank you for asking. Emily asked whether we have experimental data on the wiggle well or finite germanium concentration theory that Sue Coppersmith presented. And Emily, yes, absolutely we do. We are actually in the final stages of finishing up a manuscript on exactly that. And this is a close collaboration with Sue, with Mark Friesen, with Bob Joint. And the lead author on that paper will be Tom McJunkin, who just graduated from my group and is at NIST now, doing a postdoc there. And so, yes, and not only that, but we're continuing those experiments. So the data we have so far is on the what we call the long wavelength wiggle well, which is a period in germanium oscillations, which is all of 1.8 nanometers. It sounds kind of short wavelength to me, but nonetheless, that's the long wavelength one. And we are just now setting up an experiment to measure the short wavelength wiggle well, which is also really exciting. So yes, thank you for that.
Thank you. Other questions? If not, let's thank Mark again for a wonderful talk. Thank you for being here virtually, but.
Yes, thank you for having me virtually. I really appreciate it.
Thank you. So our next speaker is Will Oliver from MIT Lincoln Lab. So Will Oliver is a jointly appointed professor of electrical engineering and computer science, physics, and Lincoln Laboratory Fellow at the Massachusetts Institute of Technology, MIT. He serves as the director of the Center for Quantum Engineering and associate director of the Research Laboratory of Electronics. Will's research interests include the materials growth, fabrication, design, and measurement of superconducting qubits, as well as the development of cryogenic packaging and control electronics. Will is a fellow of the American Physical Society, senior member of IEEE, serves on the National Quantum Initiative Advisory Committee and the U.S. Committee for Superconducting Electronics, and is an IEEE Applied Superconductivity Conference, or ASC, board member. He received his PhD in electrical engineering from Stanford University in 2003. So it's a real pleasure to have Will. Thank you, and take it away.
Thank you very much for that kind introduction. It's really a pleasure to be here. Everything looks okay on your side and sound is okay?
Yeah, everything looks okay.
All right, great, thanks. So yeah, I'd like to talk today about quantum engineering of superconducting qubits, and I'll do some basic stuff and then give a little bit of my own group's research results towards the end. Before we get into it though, I think it's a good idea to think back to the last century of classical computing development, our classical electronic computers. The vacuum tube was invented in 1906, a long time ago, and it was used for radio transceivers, amplifiers, for example. But it was a good 40 years before it found its use in ENIAC, which, as you may know, was the first vacuum tube-based computer from the University of Pennsylvania. And as you can see in the picture here, it takes up, basically the whole room. Now, vacuum tube computers went on for a while, but in parallel, the next year, 1947, the bipolar junction transistor was invented at Bell Laboratories. And within about 10 years, there was the first fully transistor-based computer called TIXO, or TX0. That was developed here at MIT and at Lincoln Lab around 1956. Now, again, takes up the whole room, doesn't look anything like the computers we have today. This basically soldered these bipolar junction transistors together to make the computer. Now, to get a step closer to where we are today, of course, we needed integrated circuits. Those were invented in the late 50s, but it wasn't until the 1970s that we actually started to see small scale processors, like a 4-bit processor, an 8-bit processor from Intel. Here I'm showing the 4004, had 2000 transistors. we'd have to go into the 1990s before we saw the Pentium Pro, which probably many of us remember, with 5 million transistors. That was a huge advent. And then you advance another 25 years to get to where we are today with multi-core processors and GPUs, each with billions and billions of transistors. So that's where we are today. But looking back, it's well over 100 years of development to get from the first fundamental logic element demonstration to the computers we have. Now, compared with that, quantum computing is still quite nascent. It's a very exciting time, but it's still pretty early on. Richard Feynman, Uli Mannin, and others in the early 80s suggested that if you want to simulate a quantum system, you should use a quantum system to do that. Basically, because there's just so many degrees of freedom and numbers to keep track of, you need a quantum system. It wasn't until the mid-90s that we started to see theorists proposing algorithms like Shor's factoring algorithm, period finding algorithm, quantum annealing and adiabatic quantum computing, Grover's algorithm, and in fact, the first proposals for quantum versions of error correction, which we can use to make our quantum computers more robust. But this was all really at the theory stage. You'd have to advance to where we are today, about 25 years from then, to get to our current status, which is that we have quantum computers in the cloud, small scale quantum computers, maybe around 50 qubits. And we even have early demonstrations of quantum advantage. And so the takeaway message is this. First off, quantum computing is real. And it's transitioning from what we might call a laboratory or a scientific curiosity to technical reality. That's happening around us right now. And there's a lot of hype. There's hype because there is promise, but there's a lot of hype. And even though there's hype, we know that advancing from discovery to useful machines takes time and it takes engineering. And we can glean that from that classical computing historical review there. Maybe another thing is that you need to be in the game to play. Even though it's going to take some time, it may be no surprise to us that the companies that are making these multi-core processors are the same ones that were in it for decades, or they bought companies that were in it for decades. So you need to be in the game to play, even though it's early on. There are a lot of qubit modalities that are candidates to build a future quantum computer. And in fact, there may be more than one as this technology evolves over time. What I'm plotting here on the left is the operations before an error occurs. That's how many quantum gates can I apply before an error occurs. And that's basically one-to-one in what we would call the gate fidelity, which is a more formal benchmarking definition. But basically, if you have one error in 100 gates, your fidelity is 99%. And if you have 1 in 1,000, that's 99.9%. That's the idea. And on the horizontal axis is gate speed. And you want to be in the upper right corner for the best performance. And this dashed red line that appears, that's the most lenient level of gate fidelity or threshold for quantum error correction that we know of today. Common one, and that's for the surface code. And of course, you want to be above that so that by adding more redundancy or more qubits together they act as a superqubit or a logical qubit, and that behavior is in fact better if you're above this fidelity. As you imagine, the individual qubits need to be at least good enough so that if you add more, things get better and not worse. Now, there are a number of modalities that have solidly demonstrated 1 qubit gates. I list them here. Now, many of these have also demonstrated 2 qubit gates. And what we need is, what they're working on is doing tomography and randomized benchmarking, interleaved randomized benchmarking to get a solid fidelity number. But they're very, very close. And then there are a number of technologies that have demonstrated both 1 and 2 qubit gates. They're listed here with the ovals. And as you know, with a handful of single and 2 qubit gates, one can perform any arbitrary quantum logic. That's why this is an important metric to keep track of. And you can compare them against one another, as you see here. The 2 leading candidates today are trapped ions. These are some folks here at MIT working on this. And superconducting qubits, which is my own research along with my colleagues. And both of these have large teams here at MIT and Lincoln Lab supporting it. In a nutshell, trapped ions are trying to make a higher fidelity 2 qubit gate. They're also trying to just, in general, make the gates faster. And for superconducting qubits, we're relatively fast already, and we're trying to improve both the single and the 2-qubit gate fidelity, right? And so which one is the winner? I don't think we know yet. And again, as this technology evolves, it may be that we have, different eras and different winners. And one other thing we can say is that the field moves very fast. And since I made this chart maybe 1.5 years, 2 years ago, all of these 2-qubit gates have basically improved by about an order of magnitude. There are other technologies, of course, not just superconducting qubits and trapped ions, but we have NV centers in diamond, neutral atoms. The NV centers, they really shine as quantum sensors, right, of magnetic fields, for example. And neutral atoms are really great at simulating Hamiltonian, particular lattice models. And so here are some colleagues on the top doing neutral atoms and some doing NV centers. I'm just about to start silicon quantum dot effort, collaborating with Mark, who we just heard from, and also HRL. I'm really excited to get going on that. But again, the takeaway is that, look, there are lots of technologies under development to realize the promise of quantum computing. Okay. And if you look at what does a quantum computer look like today, what I'm showing here are several examples of superconducting technology. So on the left here is Google's Sycamore processor. We'll talk a bit more about that one later. Here's one of IBM's processors from a couple of years ago. This is 16 qubits. Here's one of Rigetti's 20-qubit processors. This is the backside, so the packaging of an Intel processor. We don't see the processor here. This is D-Wave's quantum annealer. This is a different type of quantum computer, one that focuses on classical optimization problems. It doesn't have as much coherence, but it does have a much larger qubit count, as large as 5,000 qubits. So that's for quantum annealing. But all of these quantum computers, I would say, are at this stage of development. This, of course, is not a quantum computer. This is the Wright Flyer, which is, as you may remember, was the first plane under its own propulsion and, with a human being on board steering it, was able to fly. Now, this plane, it tried several times. A few of the times it flew maybe 600 feet, 1,000 feet, maybe you could almost touch it. It wasn't that high off the ground. A couple times it crashed, took a couple weeks, So it was really just sputtering, getting the engine to turn over and run. It was at that level of development. And I believe that that's really where we are, and there are other analogies here, which I think are quite valuable. One is that, this demonstration didn't solve a critical transport problem. Sure, we have airplanes today, but we still have trains, we still have ships, we have automobiles, right? So quantum computers aren't going to replace classical computers, they're going to augment them, right? And that's one analogy. And the other is that, this demonstration happened, but it wasn't as though the next day everybody went out and bought airplane tickets and went on vacation in Hawaii, right? So this was a very important demonstration, but it would still take 1, 2, 3 decades, right, of engineering and development to get to the point where we had commercial airlines, for example. So to realize the promise of quantum computing, and there is a lot of promise, we need to engineer quantum systems that are robust, reproducible, and extensible. And we're doing that right now, and it's going to take a little bit of time. Okay, so with that as an introduction, let me tell you a bit about superconducting qubits, engineering these systems in general, and then some work we're doing on 3D integration. So superconducting qubits are basically LC circuits. Excuse me. If you take an inductor and a capacitor, put it in parallel, it's a parallel LC circuit, has a resonance frequency of 1 over the square root of LC. And if we cool this resonance circuit down to a low enough temperature, how low? Well, an energy scale kT, where T is the temperature, being much less than Planck's constant times this resonance frequency. If you're in that limit, this circuit is quantum mechanical, right? It's a harmonic oscillator, has a parabolic potential. It has discrete energy levels, and we can label them 0, 1, 2, representing the excitations of this harmonic oscillator. Right? The voltage and the current, they don't commute at this stage, right? So it's really a quantum mechanical circuit. But it's not a qubit yet. And the reason is that the 0, 1 transition and the 1, 2 and the 2, 3, they're all degenerate in this harmonic oscillator. So to make it a qubit, we need to add a nonlinear element. And we could take the capacitor or the inductor, doesn't matter. But in the field of superconductivity, we have conveniently a nonlinear inductor. And that's formed by a Josephson junction, which is two superconducting leads interrupted by a thin insulating barrier. Now, in this case, this is an aluminum oxide aluminum barrier. And Brian Josephson identified the Josephson equations for current and voltage, which I won't go into in detail today, but what I will say is that if you combine current and voltage in the usual way to define an inductance, what you find is that that inductance is highly nonlinear in the current that is passing through or tunneling through this junction, right? And that's what we need, is a nonlinear inductor. And so by replacing the inductance with the Josephson junction, nonlinear inductor, this LC circuit is no longer a harmonic oscillator. We call it an anharmonic oscillator. The potential profile is no longer a parabola, but instead a cosine potential in this case. And because it's a cosine, the level separations between 0 and 1 and 1 and 2 and 2 and 3, they differ. And they differ in a way that now we can just basically put a box around 0 and 1 and call that our qubit, right? And the degree to which the 1 and 2 transition is different from 0 to 1, that's a good thing. More different is better. And we call that anharmonicity. So there's a large family of artificial atoms, if you want to think of it this way, that are built from this concept. And we make them by adding inductors, capacitors, JJs, but it all boils down to this concept. So here's the one I just talked about is called a fixed frequency transmon, but I've illustrated here a number of different, I guess, innovations that have been made over the years, and they can all be generalized in terms of what we might call a generalized flux qubit. One big innovation is to take the junction and split it into two junctions. They don't have to be the same area, but two junctions that form a loop that we call a squid. And by putting a magnetic field through that loop, we can tune the 0-1 transition frequency. That's just one of the innovations, right? In fact, there are many design parameters, such as the critical current of the junction, the capacitance of the junction. We can add an additional capacitance, as you see here. We can add more junction array in an array. We could even add a physical inductance, et cetera. These are all design parameters that we can use to tailor the properties of the qubit that we want. For example, the 0-1 transition frequency, the degree of anharmonicity, or the sensitivity to different types of noises and in the environment, and we can trade them off for one another. And so you might think of these different qubits as different artificial atoms in a artificial Mendeleev table of elements. Now, we choose the frequency to be about 5 gigahertz, and we do that because it allows us to control them with microwaves. But that has an implication on the temperature at which we measure them. And that's because 5 gigahertz, if you think of h bar omega or HF, has a thermal energy of about 250 millikelvin. If you equate that energy to KT, the T is 250 millikelvin. And that means that a qubit at 5 gigahertz at 250 millikelvin environment, the environment would just simply drive transitions, and we don't want that. So we need to be much colder than that, and it's enough to be about a factor 10 because this all happens in an exponent. It's an Arrhenius function. So if we operate at 20 millikelvin, basically the qubit's always in its ground state if we put it in the ground state. And to do that, these temperatures, about 100 times colder than outer space, we use refrigerators called dilution refrigerators. Now, 40 years ago, this was the research experiment, right, for a PhD, but today these are commercially available refrigerators, basically turnkey. The size here is about 0.5 meter in diameter, 0.5 meter deep, so very large region or volume at 20 millikelvin. And you can see things in here like mini circuits, filters, some that we build ourselves, packages, microwave lines, attenuators, switches, et cetera, all operating at 20 millikelvin. Now, of course, we need to engineer and build and manufacture these, and we do that using lithographic techniques that we have from CMOS. And in fact, the etch techniques, the deposition techniques, they're all CMOS compatible. And one other thing to say is that this is a silicon technology. The metals we use, like aluminum, titanium nitride, are compatible with CMOS foundries. And we use silicon wafers, right? And we use the same tool set. So this is absolutely a silicon technology. What I'm showing here is a 200 millimeter wafer with lots and lots of qubits on it. If we zoom in on one chip, here are 5 qubits in a row. And you can see some readout resonators up here and some control lines down here. Zooming in on one of these qubits, this plus is actually the capacitor. This is one of the plates and the other is ground. So it's a lateral capacitor. Zoom in further and you can see the inductor. That's this little piece right here. The inductor is this loop, a squid loop with 2 junctions. Again, a magnetic field through this loop lets us tune the 0-1 transition frequency. And then zooming in further is a Josephson junction itself. That's what's shown here at the 200 nanometer scale. We control the qubits using microwave pulses. And so it's basically based on microwave engineering or IQ mixing. And that's shown here. Using commercial gear, for example. An IQ mixer has an in-phase and a quadrature port, and it also has an LO port where we put a local oscillator that's close to the qubit frequency, and the mixer will multiply that by the pulse that we put in the I and the Q port. And those pulses are at a lower intermediate frequency as well as have an envelope. What comes out is the sum and difference, right, of those frequencies. And this would be, one of these is resonant with our qubit transition 0-1. And you can also see that it has an envelope. Now, the last thing is the difference between I and Q. I is in phase, so that will rotate around the x-axis. Q, if we decide to use that port, that'll rotate around the y-axis. And so what I'm showing here on the left is a block sphere. The north pole is 0, the south pole is 1. This blue vector is the state of the qubit. And the red arrow that comes in and out is reflective of the pulses that are illustrated on the right. Just the envelope is shown. And I apologize, the colors aren't coordinated, but blue on the right means an I port, and that's a rotation around the x-axis. Here it's around the minus x-axis. We're going to rotate now around the y-axis. And with half the area, we only rotate half as far. So that's a 90-degree or pi/2 pulse, takes us to the equator, and then back up to the North Pole. And so this is how we can control superconducting qubits with just standard microwave gear. Using that, we can achieve gate fidelities, and the fidelity of a single qubit gate is basically how close to the desired gate did we get. You know, think of it, if I go from the North Pole to the South Pole, how close to the South Pole did I get, meaning how good was that gate? This is from interleaved randomized benchmarking, which is a benchmarking protocol. And you can see that all of these different gates, whether it's around the x-axis or the y-axis, the z-axis or the identity, are all at least 3.9, so at least 99.9%, a little bit more. Our 2-qubit gates, the fidelity here is, these fidelities are greater than 99.5%. On an I-swap gate, our best is almost 3.9s. And on the controlled Z gate, our best is about 99.8%. And you can read more about these in these papers here. But with a handful of single and 2-qubit gates, we can perform arbitrary quantum logic. They're universal. And of course, to do that, we needed to improve the coherence as well, not just the microwave engineering. And over the last 20 years as a community, superconducting qubits have improved the coherence from nanosecond scale out to and exceeding 100 microseconds. These are some times for different types of qubits that we've achieved here at MIT and Lincoln Lab. And again, the improvements over these years has been due to a combination of material science, fabrication engineering, and design by groups worldwide. And if you'd like to learn more, here are a few review papers that talk about this. So we saw earlier the Sycamore chip, and that's shown here. This is from Google, and arguably the first demonstration of quantum advantage, or quantum supremacy as they called it. And what you see here are 53 qubits with tunable couplers in between the qubits, and those are basically to turn on the interactions between the qubits. This was quite important, and this tunable coupler was a design that we had proposed in 2018, and it was important because it allowed them to calibrate this large array of qubits. If the coupling's always on, it's very hard to just isolate one qubit and calibrate it and its couplings. And the experiment that they did was to generate a random number, right? And what that was is that they had 53 qubits, right? And they could increase the number of qubits that they're using. And they could also increase the number of cycles or the depth of the circuit. And the circuit was basically to apply random gates, single qubit gates and 2 qubit gates every cycle for up to 20 cycles and up to 53 qubits. Now, for fewer qubits and for fewer cycles, they could actually simulate these results on a classical computer. They could use a classical computer to simulate what the quantum chip is doing. But as you might imagine, as you get to larger numbers of qubits and larger numbers of cycles, if a quantum computer can have advantage over a classical computer, at some point, the classical computer just can't keep up. And that's what they showed is they compared their 53 qubit chip, which could, in about 200 seconds, sample this random distribution at the output using about 50 kilowatts of power. And they could compare that to the #1 supercomputer in the world, and that's the Summit computer at Oak Ridge National Lab. That computer, by the way, has 10 to the 17 transistors compared to 53 qubits, right? 40,000 processors, that is. It uses hundreds of megawatts of power. And depending on which algorithm they would use, it would take anywhere from a couple days to much longer for that system to sample and simulate what this quantum computer is doing. So this is clearly a demonstration of advantage of a quantum computer, 53 qubits and 50 kilowatts over, a supercomputer, right? One of the best computers in the world, the best computer in the world. So that's what they demonstrated, and so it's an initial demonstration, but it's very early, right? This is not really a commercializable algorithm per se, but it is a demonstration of quantum advantage. Okay, so with that, I'd like to move on and talk a bit about engineering quantum systems and how we might do that. So any system needs an architecture, and the architecture, this one's due to Cody Jones, that I'm showing here has basically 5 layers, okay? And you can quibble about the names and stuff, but the top layer is something like an application layer where you have a human-computer interface and we type in an algorithm to that interface, right? And then a logical controller interprets, compiles what you've done and converts that into a series of gates which are applied to the qubits, the physical qubits. They're at the bottom layer. But you see these other 2 layers in between, and they're both related to protecting the system from errors. And one is a passive error suppression layer, and one is an active error suppression or error correction layer. And our qubits today, as I said, it's 1 part in 1,000 to 1 part in 10,000 error rates. That's 1 error in 1,000 to 10,000 gates. Transistors, on the other hand, their errors are better than 1 part in 10 to the 20, right? So they almost never fail. So there's a large difference between where we are today and where we need to be to do useful algorithms. We don't really need to be at 1 part in 10 to the 20, that'd be nice, but we need to be at about 1 part, say in 10 to the 10 or 10 to the 14 to do commercial scale, large scale algorithms that are sustainable over long periods of time, much longer than the individual lifetime of any single qubit. And so to do that, basically you need the controller as well as these active correction and suppression layers. And on every clock cycle, we need to be not only implementing the algorithm, but we need to be passively suppressing errors and also checking if that suppression is not perfect, checking if they occur additional errors, and when they do, correct them. So I'd like to give a physical intuition for this. I like to use this analogy of lacrosse, which works pretty well, I think, to look at these first 3 layers. We'll start with the physical layer. And so this person here wasn't very happy when I asked him to do this because he's going to show you how not to play lacrosse. Lacrosse has this stick, and as you know, there's a ball, and you want to keep the ball in the basket while you run down the field. But as you run, your body bounces, so that's one source of noise. And the environment, the grass, the ground, also has bumps, and that's noisy. And so the result is the ball just falls out very quickly that we have an error. And that's basically the physical qubits that we have today. But just as we don't play lacrosse this way, we don't operate our physical qubits this way as well. What we do is something called passive error suppression or dynamical decoupling. And what that is we cradle the the stick back and forth, 180 degrees, back and forth and back and forth. We're not thinking about it. We just do it because we know that that's a good thing to do. That decouples the noise of our running. It also decouples the noise of the ground so that the ball stays in the basket, right? And then you can go down and score a goal. All right, so that's what you do, but it's passive. There's no active, you're not measuring if something happened. You just always do it. You always do this cradling because you know it's a good idea. All right, and that gets rid of a lot of errors, but not all of the errors. Just like in quantum computing and lacrosse, you'll occasionally have a defender, the big D, decoherence, comes up behind you and just simply knocks the ball out, right? Passive error suppression doesn't prevent that. That does happen, and when it does happen, you need to first identify that an error occurred, where it occurred, and the type of error, and then you go pick the ball up again, and then as soon as you do that, you start cradling and doing the passive error suppression again. This is what we need to do in a large-scale universal quantum computer. Okay. So that gives an idea of what we need to do, and let me tell you a bit about where we're at with 3D integration and working towards that goal. So superconducting qubit arrays, I've already shown this picture once, and our coherence times are around 100 microseconds. The fidelities are 3 nines or a little bit better. And we're currently measuring circuits with 3x3 arrays and 4x4 arrays of qubits. And what you see here is a 4x4 array, and each one of these islands here with 2 rectangles, that's a qubit, so there's 16 here. And you see a lot of the control lines and the readout lines around the outside. And what you can see is that there's just not enough room to get additional lines into the middle, at least not in plane. So what we have to do is use wire bonds and jump over, basically break the plane. But that's not great either, because we know that this will, not impedance matched. And of course, what we really need is 3D integration. We've been working a lot on that. Let me just tell you a couple of quick results here from work in our group using a 3x3 array. One is to do quantum random walks in 2D. And if you live in Manhattan or have lived there before and you want to get from point B to point A, if you're a bird, of course, you just fly in a straight line. But in Manhattan, you have blocks. And so you have to basically take left turns and right turns. And you can count the distance, say, from qubit 1 to qubit 9 by how many steps you need to take. So this would be 1 step, this would be 2, 3 steps, and then 4 steps to get to number 9. Okay, so that's what's plotted here on this axis, is the number of steps. And this axis shows the evolution time. And we start with an excitation in qubit 1, and we watch how it goes to qubit 9, and then it comes back and back and forth and back and forth. This is experiment. This is simulation on the right. And you can see that they match very, very well. So what this is the Bose-Hubbard model. And what that is that you have an on-site energy. Each qubit has an energy, and we can tune each one of those energies. Now, in this experiment, they're all degenerate, but we can tune them individually. There's also nearest neighbor interaction between the qubits. That's how we take steps. And then the third is that there's an on-site interaction related to the n-harmonicity. And that's basically, in Bose-Hubbard model, that's called U. We're in the limit where U is much larger than the interaction strength J, and that's called the hardcore limit. It's a strongly interacting limit. Okay, so each qubit is either empty or occupied with 1 excitation. All right. So we've observed, in going from 1D to 2D, we've observed a quadratic speed up of the propagation of quantum information across a lattice. And we've been working on multiple excitations, localization, and something called OTOX, out of time order correlation measurements. So we have a paper that's about to come out in Nature Physics on this. But let me just talk a little bit about the localization. One nice feature of these lattices is that we can control the energies of each qubit individually. We can read them out individually, right? That's a strength of our system. So we can set disorder to random values at will. And what's plotted here is the disorder strength normalized to the coupling strength J. And then what's shown here is participation ratio, but it's basically a definition of how the excitations spread. And so we do that for 1D Anderson localization, where we excite number 7 and we ask how far it can go. Or in 2D, we excite number 7 and ask how far this excitation can go. And what we see is that this excitation spreads more and more as the disorder gets smaller and smaller, as you'd expect. And so what you see here is data, a theory fit, as well as just simulation of our system. And you can see that they all agree very well until you get down to the lattice size limit. There's another type of localization called Wannier-Stark localization. And here you can think of it as having a field or a gradient applied to your lattice or your 1D or 2D lattice, right? And so in this case, with 1D, we have an excitation at number 2, and we ask, how does it spread along the left and the right arms? And in the local, when you're localized, what happens is the excitation starts at 2, and as a function of time, it tries to go to 1 and 3 and onwards, but then it quickly comes back to 2 because of this gradient. And it oscillates like this. It goes away and comes back and goes away and comes back. And these are called block oscillations. And when we see that in 1D, we also see it in 2D. And then here's a 1D Stark localization example. All right, here it is for 2D. Now we have 2 gradients that we can apply. You can see the block oscillations when we excite at one of these qubits, in this case number 9, and how it tries to go away and come back. And again, we're showing here that the data fits simulation very well. And since I made this slide, we actually have a little bit better data now. Okay, so you can read more about these on the archive papers. But what we're doing is we're taking these 2D arrays, and of course we want to measure them and in fact go to larger sizes. Through a very generous donation from Keysight Technologies, we're currently building with Blue Force a refrigerator that can test up to 64 qubits. Now, we're not going to run out and test 64 qubits right away on one chip. What we're going to do is take a couple of these 16 qubit chips and test those. But this will give us a test bed that with room to grow, and Keysight has provided this generous funding to allow us to do this. So, but what we need to do is 3D integrate, and through the IARPA Quantum Enhanced Optimization Program over the last 5-6 years, we've been developing 3D integration technologies. And what we call it is a 3-stack, because we have three chips which we join or stack together, as you see here. The top chip is the qubit chip. The middle chip is an interposer with through silicon vias that can carry signals up and down through the wafer. And at the bottom is a readout and interconnect chip. This is a multi-layer, think of a California highway system of wires going over and under each other, that can take a signal from the edge of our package and through this chip into where it needs to go under the qubit it wants to address, and then it comes up through the TSV to address that qubit, right? Now, the features of this approach, and the reason we did it this way, is that the qubit chip and the interposer use high quality silicon wafers, right? It's basically intrinsic silicon, so high Q silicon, which means that the coherence times aren't impacted, even though we add another dielectric silicon nearby. Now, this also affords us another layer on which we can build qubits or couplers, coupling elements, and so that's an advantage. And another innovation was this through silicon via, and I'll show you a picture in just a moment. Okay, but we do it this way because we can fabricate these separately, optimize for their purpose, and then join them together in the end. Now someday we may learn how to do these monolithically, but today that's very challenging. And so fabricating them separately is the way that's our approach. So as I said, the top chip is in fact this superconducting qubit chip, in this case 16 qubits. We would flip it over for flip chip. The middle chip or wafer here is the interposer. And what you see here are these small high aspect ratio through silicon vias, about 10 or 20 to 1 aspect ratio, so 10 or 20 microns by 200 microns deep. They're lined with titanium nitride, and they superconduct below about 2.5 Kelvin. So these are superconducting small form factor through silicon vias. And this has since appeared in NPJ quantum information. Now, using these vias, we've demonstrated that we can route signals to the qubits and read them out. And the qubits have T1 times shown here around 40 microseconds. So flip chipping this together hasn't degraded the coherence times very much, if at all. And the other thing that we have with these through silicon vias are another advantage is that we can make readout resonators. I didn't talk about that, but we use resonators to read out these qubits. And currently they're in the same plane as the qubits, so they're taking up even more space. But we can hide it as a lumped element underneath the qubit and then reach up with the TSV to couple to the qubit capacitively and thereby read it out. So 3D integration doesn't just allow us to route signals where they need to go and get them to the qubits, it actually saves space. And we have a number of examples like this, which we're hoping to publish in the coming years, where we show how 3D integration saves space in superconducting qubits. This bottom layer is a multi-wiring layer. This is a niobium process, in fact. The light gray are the wiring layers M0, M1, M2, up through metal layer 7. You can see there's vias that connect those wiring layers together. You notice that they're planarized as well, and we need that for high yield. We have active elements, JJs here, as well as resistors and contacts, right? And so we can use this for parametric amplifiers that use JJs. We also use it for classical digital superconducting electronics called single flux quantum or SFQ electronics. We haven't done that yet. We've just basically used these for the routing capability to get the signals where they need to go, as I've described. But one could imagine using this in the future for those purposes as well. So just wrapping it up, all of this takes quantum engineering, and quantum engineering is a big discipline. If you think of it as a university, it's both the School of Science and all those departments, including physics, math, chemistry, probably biology, and others, computer science, which is also sometimes an engineering department, as well as electrical engineering, material science, here's control and DSP, analog digital circuits, chemical engineering, mechanical engineering, et cetera. And all of these disciplines, they have expertise that we need to bring to bear for quantum applications, but they all need to pivot to the needs of quantum test beds and future quantum systems. And so that's basically how I would define quantum engineering. It's the bridge or the pivot that needs to be done, the abstractions that we need to make so that people from these different disciplines with their expertise can apply that expertise to the development of future quantum systems. And that is quantum engineering. So with that, let me acknowledge my many colleagues at Lincoln Laboratory, as well as down at the MIT campus in the Engineering Quantum Systems Group, as well as the many sponsors who make this work possible. And thank you for your attention.
Thank you so much, Will, for the amazing talk. So questions from the audience? Yeah. Please come up to here. Microphone.
Yeah, first I should apologize. I'm a total novice in all this, and I really am just struggling to understand any of it. But you quote an error rate of like 1 in 1,000 for the qubits, I think, and 1 in 10 to the 20th or whatever for regular transistors. You need much less qubits, obviously. They're running with 50 qubits compared to 10 to the 17th. What I'm trying to reconcile what the failure rate of a qubit is relative to the failure rate, the impact of the failure rate of the qubit to the impact of the failure rate of the transistor on the overall operation of the system.
Yeah, great, thanks. That's a great question. So basically the idea is that you need qubits and you need to have them remain coherent, no errors, long enough that you can apply all the gates you need to do a quantum algorithm. And if that quantum algorithm has a circuit depth of 20, like in Google's demonstration, right? So that's basically 20 gates and I'm done, then you can just barely do it with the qubits that we have today and the error rates that they have. So Google had error rates between 1 in 100 and 1 in 1,000 in their demonstration. And they had 53 qubits and they applied 20 cycles of gates, right? Now, if you wanted to do a commercializable, or at least as we know it today, commercializable algorithm, or say Shor's algorithm, or a quantum chemistry simulation, you would need, thousands of perfect qubits, right? Meaning that they could run for, let's say, hours, right? Or you would need many, many more qubits. You would need error-corrected qubits, which effectively have a much lower error rate so that they could last long enough to do the computation. Of course, we don't have perfect qubits, so we need to error correct. We either need to improve the qubits that we've got to the level where they don't need error correction anymore, or we need to implement error correction. And you could ask, okay, so for a typical algorithm, how many gates do you need? What's the depth that you need? Or what's the error rate that you need equivalently? And so it's going to be somewhere around 1 part in 10 to the 10 or 1 part in 10 to the 14, right? To get to the level where we're running sustained calculations for, say, an hour or several hours, much longer than the intrinsic coherence times or the error rates of these individual qubits, right? So how do you get from 10 to the 3 to 10 to the 10 or 10 to the 14? Well, it's either making up that difference with improved qubits, which everybody's trying to do. We certainly want to improve them, but that's a tall leap, right? And so the way to do it is a combination of improving the qubits and quantum error correction. And with quantum error correction, using the qubits we have today, we probably need 1,000 to a few thousand qubits, physical qubits, acting together to make one logical qubit. So that's a pretty high overhead, right? And people are working really hard to do that. Both Google and IBM are on the record to say they're going to do that in the next couple of years. But the resources that you need to implement error correction go down as your qubits get better. I mean, that makes sense, right? If you try to do something coordinated with a bunch of kindergartners, adding more kindergartners doesn't help. It only makes the matters worse. But at some point, students get mature enough that adding more students actually makes things better, right? And so the better the qubits can become, the fewer qubits we need to achieve the same logical qubit error rate. So the resource requirements or overhead goes down. So there's still motivation, and there's definitely motivation to make our qubits better. But I don't know that we're going to make up 7 or 10 orders of magnitude. And to make up the difference, we're going to need quantum error correction. So I'm not sure if that answered your question. I think I maybe even answered a few things that you didn't ask, but hopefully that sort of rounds it out.
Yeah, that answered the question. I do have a follow-up question though. How many students do you need to get to the point where it's actually, or what age do they get to that get better when you have more students?
That's a good question. I know my son is 12 years old. I think he's right about at threshold now. So give him a few more years and adding more will make it better.
So thank you. Other questions? So if not, let's thank Will again for an amazing talk. Thank you so much.
Yep, thank you.
So we'll now take a break and be back, I think, in 15 minutes for the last session.